This is a presentation on common household circuits. This presentation is intended for my Physics PHY 6223 class at Lawrence Technological University. My name is Stephen Bornheimer and I'll be presenting this presentation. To introduce you to these common household circuits, there are several of them that I want to go ahead and take a look at today. These different circuits allow us to diversify the types of lighting mostly that we find in our homes. Most of the circuits in our homes that involve either complexity or that are not your typical circuits are mostly with lighting. Some with outlets, but most of the circuits in our home are either for lighting or for outlets. So this presentation will focus on the four different types. The first being like chandelier lighting. How is a chandelier lit? The second being adjustable or dimming lighting. Then we will look at the three-way switch and three-way light switches in general. And then we will end our discussion looking at the three-way light bulb, which we oftentimes use in lamps and things like that. So let's go ahead and get started. Chandelier lighting. This is a beautiful chandelier here in Germany. Okay, chandelier lighting is unique just because most chandeliers deal with multiple bulbs. It's kind of like the definition of a chandelier. And some chandeliers may have just a few bulbs. A lot of chandeliers have many. Some have hundreds. So what's unique about the chandelier is that when you have it lit, you do not want a single bulb to cause the whole chandelier to go out. Kind of like those really cheap Christmas lights, when one bulb, the whole would go or burn out, the whole strand would darken. Chandeliers have to have independent lights that when they burn out do not cause the whole chandelier to burn out. That would be very ineffective, and oftentimes because chandeliers have so many lights, there are going to be a few that burn out, like a Christmas strand of Christmas lights. But for the most part, chandelier lighting needs to have independent lighting strands for each individual bulb. So that's what makes chandeliers unique, and because of their design, they're often ornate. They are used in areas where we try to dine or entertain, or in areas where they're going to be high up, providing a lot of lighting to a particular, maybe to a large room or to an area. Okay, so one of the things about chandelier lighting is that it just kind of, and from our discussion on parallel and series circuits, is that it is not going to be wired in series. If it was in series, then one bulb would, if it burned out, especially if it, incandescent, would cause the whole circuit to go dead, and all of the lights would go out. And as I was just saying, that's not an ideal chandelier. So one of the things that people who make chandeliers have to be mindful of is that each branch has to act independently, which this is very much modeled after a parallel circuit. So if one bulb goes out, the remaining bulbs stay lit. Here's a diagram I drew to kind of help give you an idea of how each bulb would be wired. Now obviously this is a simplistic version and it only involves 3 light bulbs, whereas most chandeliers will have anywhere from 4 to 100. So this is meant to be just a simple representation, but it's meant to show you exactly how these branches operate independently of one another. So one of the things that I want to bring your attention to here is right here in the center of this kind of the screen, there is this red branch, and that is the hot wire, the live wire. And what you'll notice is that it simultaneously feeds all 3 branches of this model chandelier. Okay. So then what we have happen is that the hot wire feeds up into a branch here, here to the left in branch 2 and in branch 3. And it then goes through the light and then back down and feeds into the other wire, sometimes called a neutral, which then goes back into the wall. So we see here that each branch is kind of completing its own individual circuit. However, all 3 branches are being fed by the same line. So typically speaking, what happens is that each branch is fed with an equal amount of current, which is why all the lights, when they are turned on in a chandelier, shine with the same intensity. However, this also means that you have a lot of resistors. And because each branch acts independently, you have to be mindful of how much draw or how much resistance each one has, because in a parallel circuit, the more resistors you have, the more current is going to be drawn through. So one of the things that you will see oftentimes in a chandelier is you will see very, very small light bulbs. Not big. You won't have 5 or 6 or 7 75-watt light bulbs. The reason being is that the resistance being much greater would cause the entire circuit to exceed exceed its current. And most lighting circuits are 15 amps. However, that usually runs anywhere from a couple of rooms to maybe a third of a house, depending on what size house you have. So you have to be very mindful of the fact that you don't want a chandelier to have what could be, in essence, more than the amount of lights you would have even on an entire house. So when you build a chandelier, they oftentimes build them with low resistant light bulbs, just a couple of ohms. So that way, when you have a lot of lights and they're all shining with the same intensity, you're still getting that nice ornate glow that a chandelier would present in a particular space. So that's one of the challenges that a chandelier presents, is you have to be very mindful that because each branch does kind of act like a parallel circuit or branch of a circuit, that there's going to be a very large draw of electricity here. Okay, so that's chandelier lighting. And now we're going to talk about adjustable or dim lighting. You may have seen those knobs if you've ever walked into a house. It's a little knob switch and you tap it and it turns the light on. But then if you twist it, it will actually dim the light or make it brighter. And so one of the ways that this works is with a switch like what you see on the screen. And how this works is that there's actually a very large amount of wire stored in this switch, and we're going to take a look at why that makes such a difference in the way the lighting works. Okay, so to understand basically how dimming works, because it's not just in our homes, it's actually a crucial aspect of theatrical lighting. And one of the things that you have to look at, or you have to recognize, is that wire itself has has some resistance. And that resistance varies with wire size, or as what we call in the industry gauge, but also with how it's coiled and things like that, and its temperature. So typically speaking, the more wire electricity has to, or the more wire electricity has to pass through, the more resistance it will encounter, because more wire means more resistance. Inherently, wire has resistance. So in order to get a lot of wire into a very small area, like a little dimming switch that you would maybe put in a receptacle, they coil it. Okay, so coiled wire that acts kind of like a resistor, actually is a resistor, is called a rheostat. And here's a short film that kind of shows how a rheostat works. Okay, I'm going to go ahead and play it. Hopefully you'll be able to hear it. So we'll go ahead and give this a try.
Wires with alligator clips, bulb, 4.5-volt battery, thin wire, strip of cardboard. Wind the thin metal wire in tight coils around the cardboard strip. Connect the wires to the battery, connecting the tip of one of the wires to the metal wire on the cardboard, leaving the other one free. The rheostat is ready. Look at the wiring diagram on the screen. changes. It is more intense when the clips are closer and less intense when they are far. The rheostat is a variable resistance. This means that there is a resistance to the electricity that passes. The resistance increases when the number of spires between the two clips increases. Therefore, the more spires there are, the less current passes, and less intense is the light of the bulb.
Okay, so one of the things that the video shows well is basically how this coiling of wire that creates resistance works to change the intensity of a light bulb. So what we're going to do is we're going to kind of break this down a little bit. Okay. Imagine for a moment that we were to take 3 snapshots of a large coil, and we were to say that the first coil, like this diagram at the top, had 10 ohms of resistance, had a lot of resistance. Then if we were to move the clip a little bit closer, there were fewer coils that electricity had to pass through, that would be like a 4 ohm resistance, okay? So less wire that the electricity has to pass through. And then let's say that there's very little electricity that has to pass through, just a few coils, and we say that's 2 ohms of resistance. When you use these coils of wire that act as resistors in a circuit, and they have variable amounts of resistance depending on where your switch is contacting the coils and thus how much electricity is flowing through a certain amount of coils, it can adjust how much current is flowing through that circuit. So we'll notice here that all the light bulbs are 4 ohms, constant light bulbs, so the only resistance that's being changed is the resistance from the coils. And so what I've done here is I've used Ohm law to do a three-way comparison between what would happen if you have electricity traveling through a lot of coils, therefore a lot of resistance, all the way down to a few coils and a low resistance. And what we see using Ohm's law is that with a lot of resistance, the current is only 0.86 amps. Now this is all very theoretical, of course. The resistance is obviously vary greatly from rheostat to rheostat, as does the type of light you use and the amount of voltage in the circuit. The medium resistance, 1.5 amps, and then we see with the fewest coils, we have the most current, 2 amps, flowing through the circuit. The more current, the greater the intensity you're going to get from your light bulb. So what you can take from this is that as we adjust resistance, the total resistance of the circuit will also drop, and as it drops, the intensity of the light bulb gets brighter, and that's how we can adjust the intensity of the light in a room or a lamp or whatever by adjusting the switch. Okay, so this is a rheostat switch, and typically what would happen is you would have you would connect the switch to, say, a hot and a neutral, and then you would turn that knob on the top. There'll usually be a big old knob that slides onto that metal portion sticking up here. And as you turn it, it moves a connector inside the switch that adjusts how many coils the electricity is going to pass through. Obviously, the greater number of coils, the more resistance, the less intense the light. The fewer the coils, the more the fewer the coils, the less resistance, and the more current, therefore the greater the intensity. Okay, so that's how dimming works. Now in theaters, they have huge racks of very large dimmers. In our household, we might have at most a 100-watt light bulb, or a 150-watt light bulb. That's really pushing it. But in the theater, they're dealing with instruments that have 5,000-watt light bulbs and 2,500-watt light bulbs and 1,000-watt, 1,000-watt light bulbs. Light bulbs that have an incredible amount of power behind them. So they have a very large dimming systems, huge racks of very large copper wire coiled dimmers through which they can control the lighting intensities. And that's what allows theatrical performances to dim their lights to various levels, and to do it when they bring their lights up, for them to have such great intensities because their lights have so much power output. Their bulbs are incredibly bright, so much, and they produce, especially the old incandescent ones, produce so much heat that if you were to actually have touched the light bulb with your bare hand, the oils from your hand just being touched on the light bulb would cause the glass, because it gets so hot, to bubble. And a lot of times you have to, when you replace the bulbs in theatrical lights, you have to wear gloves, because if you touch it, even with a little bit of the oil in your hand, when used in a performance, it will actually explode. And I've actually had this happen to me. I changed a light bulb in a lighting instrument, because I also design lighting for theater, and this was in the earlier days of theatrical lighting for me. And it was a very we were in the middle of a performance, and the light bulb blew apart, and it can be very violent. It actually shattered the lens inside the instrument, so we had to actually rebuild the instrument. So, and we call light fixtures in theater instruments. So it was really a good learning lesson for me, and a great lesson in understanding more about lighting in the theater. All right, the three-way light switch. Okay, you may have one of these in your home. You might have a hallway where you have a light in the hallway and you have a switch at either end, or you might have a staircase where you have a switch at the bottom and a switch at the top, and you have a light that lights that. You might have a garage that has a light in it, and you might have a switch near the door and then a switch inside. These are often, you will oftentimes find at least one three-way circuit in your home somewhere, whether it be a hallway, a staircase, or the garage, or someplace else. Three-way light switches are very common because they give us multiple points at which to turn lights on and off. And this can be useful for a variety of reasons. Some people who have multiple access points to a kitchen might want a three-way switch in their kitchen, so that if they walk, depending on where they walk into that kitchen, they might want to be able to turn the light on. That way you don't have to walk all the way across a dark room to turn the light on. So the three-way switch is unique in that it's a little bit different. If you want a three-way or even four-way switch in your home, you have to actually buy special switches. You can't just buy a normal light switch. So this is a three-way switch, and what makes it different, or I should actually just point out those common things. First of all, most light switches will have a ground. They'll have a common, and then they'll have one of these brass screws, which is either called a hot or a traveler. Typically speaking, we call them travelers on three-way switches, and you'll see why in just one moment. Okay. What's unique about the three-way switch is it has an extra traveler, and if there was a four-way switch, it would have one right down here as well. So these travelers are going to require a little extra wiring, but you'll see why they're necessary for the three-way switch to operate. Okay. And so we're going to go ahead and take a look at the diagram on the next slide. Okay. This diagram is really great in that it shows us a couple of things. I'm going to explain it, start in the upper left and work my way clockwise. Okay, so over here you have your feed wire, that wire that would be coming from your electrical box in your home, and you have a hot wire and a neutral wire. Usually this hot wire is black, neutral wire is actually white, and then usually you have a ground in there. Okay. And what happens is your hot wire is going to feed into a switch. Now, there's a couple of ways that three-way switches can be wired, depending. Sometimes the hot wire feeds into the lamp and then down into the switches. Okay, it just depends. So this circuit can actually be reversed if you wanted to reverse the neutral and the hot, but the inner components here work basically the same way. So you have a hot wire that feeds in, and it will activate one of the lines that is the traveler. Okay, so what you see here is that these two center portions are the travelers. They travel between the two switches. So when you have a hot coming in, it will always have at least one traveler hot, period. Okay, because the switch is always going to make contact with one of the two travelers. Now, what we see in the upper left here is that the traveler that it's currently connected to is not a complete circuit. It does not go through, it goes into the second switch, but does not make contact with the wire that allows that switch to feed the lamp, and thus this switch is off. Okay, so what you notice here that the two switches are opposite one another. Okay, so this switch on the left-hand side is down, and this switch on the right-hand side is up. So oftentimes with three-way switches, what it's intended is you can have the light off, but depending on which one you flip, it will immediately turn the light on. Okay, and three-way switches are unique in that it doesn't matter if sometimes they can be flipped up and turn the light on, sometimes they can be flipped down and turn the light on. So for instance, if on this first switch you were to flip it up, okay, like you walk in a room and flip the light switch on, it would give you the scenario here on the right. Okay, it went up, it made contact with the upper traveler, which was connected on the other switch, which we haven't touched, and thus completed the circuit in red. Okay, and the light bulb is lit. Notice that the bottom traveler, it doesn't have any connections, it's just there. However, if we were to go back and turn that light switch, that first light switch off, well then, now the circuit's not complete and the light goes off. However, let's assume that we start up here in the upper left again, but instead of turning that first light switch on, we turn the one on the right here on, or we flip it down, okay? Well, then you get a scenario like this bottom right, okay, where now the bottom traveler is live and the light comes on. That first light switch didn't change, but because the second one was flipped, okay, to its other setting, it made the whole circuit live. So what we see happen here is that each switch can act independently, but in order for the light to come on, both switches have to be in contact with the same traveler. Okay, so that's how they work, and it gives us some freedom to wire a room in a more convenient way, or a hallway, or a staircase, or a garage, or a space of some kind. This type of wiring can become much more complex, and it's not as simple as this diagram shows. As you can see here, this is what could be a typical wiring setup for a typical three-way circuit involving one light and two switches. I have one of these in my kitchen, and I also have one of these in one of my bedrooms, because you can actually access the bedroom from two different locations. And mine is very much like this. When I moved into my house, all my three-way switches were wired wrong. So you could turn one switch on and it would turn the light on. You turn the other switch and the other switch would turn it off. But what happened is one of the switches was actually a master for the power. So when it was off, nothing worked. I could flip the other switch all day long and it didn't turn the light on, which means that the travelers were not connected correctly. So one of the ways that this is done is it really works best if all of your wiring is color-coded or labeled well. That is not always the case. Sometimes you'll get into an old circuit box and you'll realize all the wires are exactly the same, and this is where it helps to have some kind of test light or some kind of meter that you can check for connectivity. So anyway, I'm going to go ahead and explain this diagram a little bit. Here we have a wire. It is your typical probably 12-2 wire. What would be typical, actually, lighting uses 14 gauge wire. So typically, because lighting circuits use 14 gauge, which is a little bit of a smaller wire, because they're usually only 14 amp circuits or 15 amp circuits. If you go downstairs into your breaker box or upstairs, depending on where your breaker box is, and you look in there and there's a 15 amp breaker, or a 15 amp fuse if you have an older home that has a fuse box instead of a breaker box. 15 amps is your typical home lighting, circuit. Outlets, however, because you can plug things into them and the power can vary greatly, they are usually 20 amp circuits. They usually can handle a greater amount of current. However, they also require a little bit larger gauge wire so that they don't heat up as quickly, and usually use what they call a 12 gauge or a 12-2 wire. So this would be a 14-2 wire, and what we see happening is that it's really feeding up into this box a white, which we can kind of see here coming up, a black wire, which is actually going to go right straight to this light switch, and a green wire. And actually almost every circuit in your home should have a ground of some kind. Okay, so all the green wires we're actually going to ignore for the sake of this presentation because they're just grounding wires, and they help protect your home in the case that there is an overload of current or whatever. They are it's really important to have grounds, but that's another discussion. So you have a neutral, and notice that it bypassed this white wire coming up into the box on the left, and notice that it will continue up. It goes into a wire nut, which is just a way of splicing together two different wires, and then it goes straight up and it connects to the light bulb immediately. So that's what we call the neutral connecting to the light. And if we look here, it's basically the same thing as a neutral, as labeled, connecting directly to a light. Okay, so it's actually very much the same type of setup as this. We have a neutral connecting directly to the light. So the neutral connects, okay? Coming up into this thing, there's a hot wire that's feeding the switch. And that's very much like the hot wire that's coming in and feeding this first switch. Okay, so then we have a black and a red wire that come off and come up. The black and the red wire then continue on, okay, but what we see here is the black wire feeds into this wire nut up near the light and turns into a white striped wire. So from this upper junction box, we have a red and a white striped wire that are going to carry the hot load all the way over to this other light switch. Those are our two travelers. Okay, so those are the two travelers that you can flip between depending on how you want power to be delivered to the light. In order to complete the circuit, then you need to take one of the hots and you need to deliver it back to the light, and then the neutral obviously goes in and out of the circuit. So we have a complete circuit just like it's diagrammed here. We have two travelers going between the switches. We have a hot feeding into one switch. We have that then feeding into the light, then the neutral carrying it all the way out. So that's what we have going on here, though this is a more realistic representation of the exact same thing. Okay, so the first thing to understand with this is that it can be very complicated and that there are variations on it. If you have ever been in a home or have a home and you need to rewire a three-way switch, it's really not very difficult. However, I would definitely, it's considered a more advanced thing to attempt. So I would definitely do a lot of research and make sure you have the proper equipment. And if you are not very comfortable, then definitely hire an electrician, because it can be very complicated and you don't want a short circuit, which could be really dangerous. So one of the things, well, I guess a short would then trip your breaker, but you don't ever want to create a short intentionally. There's a great link here that can take you to a website where they have variations on three-way switches and even more complex ones. And it's a great website, and it's where I actually got this diagram here. Okay. All right, on to the three-way bulb. Okay, the three-way bulb is a little different than the three-way switch in that oftentimes we find three-way bulbs in like lamps. So if you've ever had a lamp where you turn it on and it's kind of dim, and you turn it up a little bit and it gets a little brighter, then you turn it up all the way and it's like super bright, and then you can flip it one more time and it turns off. I have a touch lamp next to my bed that does this. I can touch it 3 times and it goes boom, 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 and it gets really bright, and I touch it one more time and it turns off. So that's what we're dealing with here. Okay, three-way bulbs are quite common. For the most part, most three-ways are still incandescent, which is different. We've seen a lot of CFL, or those energy efficient spirally bulbs. However, incandescent bulbs still very much dominate the three-way arena for a couple of reasons. And the first being that there are actually multiple filaments. It's very hard to vary intensity with a CFL bulb. However, in a normal incandescent, you can put multiple filaments in that bulb, and that allows you to create multiple intensities. So in a three-way bulb, you have a 50-watt filament and a 100-watt filament. And when you have just the 50-watt filament on, you get that 50-watt low light. So it's kind of like your mood lighting. And if you flip the switch one more time, it turns that one off, turns on the 100-watt filament, which gives you that nice, bright 100-watt light. Good for reading, but not overly intense. However, some people really like the really bright light. Maybe those people that have a hard time seeing, or people that just like to have that nice bright ambiance. And so what happens is when you turn the switch one more time, it turns on both filaments, which combined together produce 150 watts of nice intense bright light. That's how the three-way light bulb works. You really are dealing with 2 different filaments. So if you see here on the right-hand side, the three-way bulb is really got two filaments. The red one being the low watt and the blue being the high watt. Notice this diagram is very simple, but the real key is the bottom of the bulb. Most light bulbs have a single metal piece on the bottom, and then there's insulator, and then you have the bulb has this area where you have the screws that's metal, and that's usually where your neutral makes contact. Okay, and that would be like right here on the sides. But on the bottom of a three-way bulb, there's actually two metal contacts separated by multiple insulators. And this is kind of what the key behind the three-way bulb. Okay, so I pulled these images offline and they're cited in the bibliography. They really are great. They were already diagrammed, and the person who did it, which is cited at the very end of this presentation, did a great job of really outlining how these work. So I'm going to go ahead and try to do this justice. You have the socket here, which would be what you would screw your light bulb into. And a normal socket has this metal ring here, number 3 on the left-hand side, that connects to the actual fixture itself. And that's usually what's touching the neutral contact if you look at the bulb on the right, that metal area of the light bulb that actually screws into the socket. In a normal light bulb, you would also have number 1 here, which is your central contact, and that would touch the medium wattage hot contact here in the bottom of the light bulb. Okay, so those two things you'll find on just about any incandescent or CFL bulb on any lamp anywhere. What makes this unique is the three-way part of it, which is the metal ring, the low wattage hot contact here. This metal ring right here on the right-hand side. That you will not typically find on a normal light bulb. Typically speaking, this will all be insulator from the hot contact, okay, for the medium all the way out to the neutral will typically be, there'll be insulator in there. This low wattage contact makes contact with number 2 over here, okay, which helps to create a secondary switch. So really what we're doing here is we have to have a special socket and a special bulb and a special switch to make a three-way light or lamp work. So it really is a very unique scenario, okay? All right, so this is an animation, and we'll see it actually go back and forth here. And I'm actually going to wait for it to kind of do its thing here. It's going to go back to off. Okay, there it is. Now when you flip it once, the switch once, it lights up the low hand side, but notice it does not connect with over here. Then it switches over to medium, but then it's not connecting here. When it's on high, it's connecting to both filaments, and now you have this great intensity. So off, okay, then you have the low filament, which is being lit only, then the medium filament, which is being lit only, and then both filaments, which are being lit, to give you that high intensity. Okay, so this is how the switch works. There are actually multiple contacts that the switch makes contact with that feed into the light bulb. Okay, we notice that the the low branch feeds this ring here, this low filament. We see it connecting right in here. The very bottom, however, is connected to that medium filament. Okay, so you can kind of just take a look. This is a great little graphic animation to help understand the three-way bulb. All right, that is the end of my presentation on the four unique common household circuits that you may or may not encounter. If you have any questions, you can go ahead and contact me at bclassroom.com. Thank you for watching and have a wonderful evening.